Most people would agree that the information revolution is a positive thing, ever-increasing knowledge at the touch of a button. But the difficulty with all this data is, where do you store it and at what cost? Well, Dr. Cameron Walker from the University of Auckland has been working on just such a question. Hi Cameron, thanks for talking to us today.
Hi.
Now, first off, how big a problem is data storage becoming?
Oh, it's huge, and not just data storage, but access to the data. Also, security of the data. What happens if when your disk dies? You want to have backup. All these sorts of things are huge issues. So what's happening is you're having cloud storage systems coming up. So the data is being centralized. Services are coming up whereby rather than storing your data locally on your computer at home, you'll be able to put it into Amazon or Google or somewhere like that, and they'll have a bunch of hubs around the world that allow you to access your data quickly, and then they'll have within their system ways of backing up and managing the data in a secure and sensible fashion, so that it's low cost or lower cost. They can start saving cost. It's means that you get good performance in terms of you want to get your data back. You may be able to get it from a number of places in parallel, sort of like a BitTorrent or something like that. So it's a big deal.
Do you think that the rate of data increase will continue, or is it going to plateau, or is this?
Oh no, it's definitely going to continue. As technology increases, the size of data files get larger. People have more personal data, movies, music, things like that. Then businesses are more reliant on data as well. No, it's something that's getting bigger. And so the kind of trend to centralise is becoming more prevalent, and so that means that again, that's just meaning that these kind of data warehouses are getting bigger as well.
So what sort of size of data storage would someone like Facebook have?
Yeah, it would be massive. I mean, places like Google have data warehouses that are bigger than football fields. And the way they manage them is not having one big machine. They're having a bunch of smaller machines. You're basically designing for failure. It's expected if you've got a disk, it's only got a finite life. It's going to fail at some point. And when you've got a large enough warehouse with enough disks, then you're going to have failure all the time. So you have to build that into your design.
So how are you involved? I mean, how does mathematics help with trying to deal with storage and keeping costs down and things like that?
Well, I mean, the fundamental problem is building a network. So you've basically got a bunch of nodes or vertices, which are like dots, like the computers, and then you're joining them up with cables, which are edges, and so you're trying to design a network which is going to perform in some way. So each edge, each cable can only carry so much data. Each node, each computer can only store so much data, and you have to come up with a way of putting it all together into some sort of network design, like a road network or a rail network, or some sort of network whereby you can get sufficient data out to meet the demands, basically, of the users.
And how do you do that? I mean, do you sit down crunching numbers? Do you use a certain type of maths to help you figure this sort of stuff out?
Well, my area is operations research, and so we're looking at optimization. And basically, yes, you build a model where you have a bunch of variables, which could be yes/no variables. Does this vertex and this vertex have an edge between them? That could be a variable. It's either 0 for no, it doesn't, or 1 for yes, it does. So you have a whole lot of variables. You come up with constraints, which are basically something like, for instance, if this computer only has 2 PCIe cards in it, it means you can only connect 2 cables to it. So the number of variables or the number of cables going into this computer, the sum of that has to be less than or equal to 2, for instance. So you have a whole lot of constraints that you also have in your problem, and basically you then solve it using some sort of optimization algorithm. So you can. I mean, I can't recall what people do at school now, but I'd expect that probably some basic linear programming is done in maybe statistics or calculus, and at maybe year 13, and whereby you kind of do something like, I don't know, I'm trying to make chairs, and I'm trying to make tables, and they're worth a certain amount of money, and I've got so much resource, and you kind of draw a plot, and this is the line for I don't know, the amount of time on one machine, and this is another line for the amount of time of another machine, and you get what's called a feasible region of solutions, and you then look at the costing of all those solutions, go, this is the best thing I can do, and it's basically the same problem. So you know, in 2 dimensions, you can kind of draw a plot, and you can actually see, oh, here's the best solution. Once you get more than 2 variables, it becomes this large multi-dimensional problem that you need to solve using some sort of algorithm. And there are algorithms that we teach at undergraduate in science, engineering, and commerce that look at solving these sorts of problems, so that you can come up with what you know is definitely the best solution given your objective function, which could be, I want to make the most profit, least cost, or whatever it might be. In particular, in our research, we're interested in trying to do things with that are sustainable. You know, in terms of energy, you want to reduce power usage. So we want to get, you know, a certain level of performance. Sure, cost is a consideration, so you can have what are called multi-objective problems, where you have more than one objective. So you could have cost and you could have power, and often the 2 objectives, you know, are going in different directions. If you like, you know, to get lower power, you might have to, well, to get higher performance, at least you'd have to use more cost, and so you have to have a trade-off between, you know, what solution do I want.
Are you working with industry on a particular project regarding this, or is this just sort of general work you're doing? Or?
Well, we work together with ITS, which is the kind of IT group at the University of Auckland. I mean, University of Auckland has one of the, well, I think might have the largest computer network in the country. So that, you know, it might seem like, oh, you know, here are these researchers at the University of Auckland working with someone at the University of Auckland, but actually, you know, ITS is the biggest client in the country. So yeah, we're doing work with them, and they're great. They give us gear to use and to play around with, and that, you know, we can data to play with as well. So yeah, that's the main group we work with on this problem.
And the sort of computers that you're using to try and develop these systems are things you can just anyone could just go and buy at a shop, or you're getting special industrial computers in, or?
Well, that's actually one of the main focuses of our work. So currently, or you know, certainly in New Zealand, what has been the way people have dealt with their data so far in large organisations is they've gone to IBM or HP or something like that, and they've bought a large monolithic one thing that deals with all their data, and you know, they perform very well. They're incredibly expensive. For a kind of small to medium-sized business, they probably can't afford it. For a larger business, you have this kind of problem where when you fill up this box, you have to buy another very expensive box. So what we're looking at doing is solving the problem from a completely different direction, which is buying small commodity gear and then trying to put it together in a clever way. And that putting together part can be difficult. Once you start getting a larger network and you've got a lot of computers, you're looking at maybe having 2 copies of data everywhere. You're looking at making sure that there are two paths to each copy of the data, so that if one particular node fails somewhere in the network, you can still get your data out. That becomes a really difficult problem to solve when it gets large, and so that's why we're interested in it, because, you know, we work in optimization. That's sort of an interesting problem for us. So we're buying little servers that are, you know, $500 from local suppliers that are low power, and trying to put a bunch of them together to have the same sort of performance that you get from one of these large $20,000, $30,000 systems.
So they're cheaper and maybe more efficient, but they kick up other problems along the way, because you've got more things to deal with, more things that can go wrong.
Yeah, and certainly, and each unit on its own will not perform anywhere near to the level of this you know, larger system. So where you can gain is if you can do things in parallel. So you can you know, I want to read some data. If I can get it from 4 places at the same time, even though each data stream is a lot smaller capacity, and you're getting things a lot slower in each one, because you're getting it from multiple places. You can, you know, the idea is you get the same sort of performance.
Well, how long have you been working on this for?
I've been working on this particular problem for about 8 years now. A colleague of mine did his PhD at Stanford in the US, and while he was there, he was also doing consulting for Hewlett-Packard Labs, and at the time they were looking at getting into this sort of area, so they had a group that did kind of storage design problems, and he worked on that for a while. It was kind of like a summer job. It wasn't actually part of his PhD, but it was something he did along the way, and then he came back here and started here in 2002, and I was here at the time, so we just started working on the problem together. Yeah, and it's been really exciting, actually. You know, we've started branching out now into the computational side as well. So we're not just looking at data storage. We're looking at smart ways of using, you know, modern gaming computers. So still just the sort of computer you go down the shop and buy, but, you know, a high-end gaming one with a decent graphics card. And instead of using the graphics card to render graphics, we're looking at using it to do computational, you know, or parallel computing, and that's looking quite promising as well. Again, the goal is to lower power. You know, it seems if you can more efficiently use one computer, make access of this really high computing resource on the graphics card, then hopefully you can solve these difficult problems that, you know, take a long time to solve in a lot less time, and so use less power in doing so.
So where are you at with the project? Do you think you're getting to an end point, or is it?
Well, so basically we bought some gear literally in the last month. One of an undergrad student who's just finishing his degree in engineering science, got a summer research studentship to work over the summer. So, you know, we've given him one of these quite flash gaming computers. He's quite happy about that. And
I was going to say, you got to keep an eye on him, make sure he's doing the research.
Oh no, he's very excited by the research. Actually, he's a bit of a maths geek, I guess, or a computer nerd, and he just loves it. So you know, he's been coming in here all excited. Oh, you know, I've been running this particular algorithm that takes this long to run when you use the CPU in series, and by using the GPUs in parallel, it's solved in, you know, a tenth of the time or something. So it's working pretty well.
Oh, fantastic!
Yeah.
So being an undergraduate can have its benefits, obviously.
Yeah, yeah.
Access to some of the best gaming computers there is.
Exactly. Yeah. Well, he's pleased anyway. Yeah.
All right. Well, thanks for talking to us today, Cameron. Appreciate it.
Yep.